The periodic table of elements is a tabular display of the chemical elements that's arguably more valuable to chemists than any piece of equipment, wonder drug, or process ever invented. The periodic table had its beginnings in the early part of the 1800s. 52 elements had been discovered by 1817, and though some had been known since ancient times, many new ones were being discovered using the energy available from the electric battery, invented by Italian physicist and chemist Alessandro Volta in 1800. It became apparent to scientists that all the elements and information about them would need to be gathered into some kind of meaningful form. During the 1820s, German scientist Johann Dobereiner noticed similarities within several groups of 3 elements, which he called triads. He found, for instance, that the properties of bromine, an element that exists as a liquid, seemed halfway between those of chlorine gas and solid iodine. In 1857, English chemist William Odling proposed that, based on their chemical and physical properties, the elements could be divided into groups. In 1862, French geologist Alexandre-Émile de Champ-Courtois was the first person to arrange the elements by increasing atomic mass, and he noted that elements with similar properties seemed to occur at regular intervals. He devised a spiral graph with the elements arranged onto a cylinder, such that similar elements lined up vertically. Unfortunately, his paper was largely ignored by chemists, since he left out the graph and also wrote it from a geologist's perspective. In 1864, English chemist John Newlands noticed that similar properties seemed to repeat every 8th element, similar to the way the notes of a musical scale repeat every 8th tone. He called this the law of octaves, and it resulted in several similar elements being grouped together. The most successful organization of the elements was arrived at independently and at almost the same time by German chemist Julius Lothar Meyer and Russian chemist Dmitry Ivanovich Mendeleev. In 1869, Mendeleev submitted a paper to the Russian Chemical Society, in which he arranged the elements into a periodic table and proposed the periodic law, which states that if elements are arranged in order of increasing atomic mass, a pattern can be seen in which similar properties recur on a regular or periodic basis. Mendeleev's periodic table gained widespread acceptance among chemists, and he received most of the credit for several reasons. His work was published a year before Meyer's, and he chose to concentrate on the chemical properties of the elements, while Meyer focused mainly on the physical properties. Most importantly, Mendeleev chose to leave several blank spaces in his table, where he predicted as yet undiscovered elements with specific properties would eventually be placed. When the elements were eventually discovered, the predictions turned out to be extremely accurate. Since 1872, many new elements have been discovered or synthesized, but the most significant modification to the periodic table occurred in 1913. Combined with the discovery of isotopes, data gathered by British chemist Henry Moseley resulted in the elements of the periodic table being reordered according to their atomic numbers rather than their atomic masses. The current version of the periodic table includes 118 elements, 92 of which occur naturally. The horizontal rows in the periodic table are called periods, and these are numbered from 1 down to 7. The vertical columns are called families or groups, and these are labeled using one of 2 schemes. One scheme assigns each column a number from 1 to 8, combined with either the letter A or B, and is preferred by many chemists. A newer system adopted by the International Union of Pure and Applied Chemistry, often shortened to IUPAC, numbers each group from 1 through 18 and uses no letters. The 2 most important things to know about the periodic table are 1. Elements in the same chemical family have similar chemical properties because they have similar outer electron configurations. And 2. As we move down a chemical family or across a period, there are regular changes in these properties, called periodic trends. Groups 1 and 2 on the left, and 13 through 18 on the right, contain the representative or main group elements. Groups 3 through 12 are the transition elements. Within the transition elements are 2 horizontal series, which are collectively called the inner transition elements. One distinction among the elements relating to their properties is their classification as metals, nonmetals, or metalloids. This staircase line separates metals on the left side from nonmetals on the right. As we move right to left across a period and down a chemical family, the elements become more metallic. About 3/4 of the elements are metals, including some main group elements and all of the transition and inner transition elements. Nearly all metals are solids at room temperature. An exception is mercury, which exists as a liquid. Metals are generally shiny or lustrous when freshly cut or polished, and also conduct heat and electricity well. Generally, they are malleable, which means that they can be rolled or hammered into thin sheets, and ductile, which means they can be rolled or stretched into wires. In the form of thin sheets or wires, they're usually flexible. During chemical changes, metals tend to give up electrons relatively easily to form cations. Moving on from metals, we have nonmetals, which are located in the upper right portion of the table. Nonmetals are usually gases or brittle solids at room temperature, except for bromine, which exists as a liquid. Solid nonmetals can range from being dull to lustrous and translucent to opaque. They also conduct heat and electricity quite poorly. During chemical changes, nonmetals tend to gain electrons from metals to form anions, or share electrons with other nonmetals. Along the staircase line are several metalloids, also called semimetals. These are solids at room temperature and generally have a metallic luster and look similar to metals. They're semiconductors, meaning that at room temperature they are poor electrical conductors, but at higher temperatures they become better conductors. We'll now take a closer look at some of the families in the periodic table, beginning with family 1 or group 1, which is located on the far left side of the periodic table. These elements, known as alkali metals, are all soft, silvery solids, and the most reactive of all metals. The oxide compounds of the alkali metals dissolve in water to produce strongly basic solutions. These metals react vigorously with water to produce hydrogen gas. The members of a chemical family have similar numbers and types of outermost electrons, which are known as valence electrons. Valence electrons are the electrons that participate in chemical bonding, and the number and type of them is primarily responsible for an atom's chemistry. Alkali metal atoms have one valence electron in the s sublevel, with the general ns1 electron configuration, where n represents the outer energy level. In chemical reactions, they readily lose their outer electron to form +1 cations, and assume the electron configuration of the previous noble gas. Chemists call this becoming isoelectronic with the noble gas. The prefix iso essentially means same. To the right of this group, we have the alkaline earth metals, which are also silver-colored reactive metals. They have 2 valence electrons and the general ns2 electron configuration. They'll readily form 2+ cations by losing those 2 valence electrons. Switching to the other side of the periodic table, we have the family of halogens, which contains the most reactive elements and is a family in which all 3 states of matter are represented. The elemental halogens exist as diatomic molecules and readily form compounds with metals, hydrogen, carbon, and other nonmetals. The halogens possess 7 valence electrons with 2 electrons in the outer s sublevel and 5 electrons in the p sublevel. When they react with metals, they typically gain a single electron forming 1- anions. When they react with nonmetals, they'll often share valence electrons. The family on the far right side of the periodic table is known as the family of noble gases. These gases are generally unreactive, although compounds of argon, krypton, xenon, and radon have been prepared. All of the noble gases except helium have filled s and p sublevels and a total of 8 electrons in their outer charge clouds. This particularly stable electron configuration, known as the stable octet, explains the low reactivity of the noble gases, and also explains the electron configuration achieved by many cations and anions. The transition elements includes groups 3 through 12 in the periodic table. All are metals and the majority are hard solids with high melting and boiling points. Many of them form cations with multiple charges, and those cations often form complex ions. A number of transition metal compounds have distinct and recognizable colors, which occur due to d-d electron transitions. The last electrons added for transition metals are placed in inner d orbitals. Zinc, cadmium, and mercury are sometimes excluded from the transition metals, mainly due to them not having partially filled d orbitals as atoms, and even in some of their oxidation states. This arises from the IUPAC definition of a transition element, but in general, many chemists consider any element in the d block to be a transition element. The placement of the lanthanide and actinide series as rows below the periodic table is simply a matter of convenience. One form of the periodic table has the lanthanides and actinides inserted after barium and radium. Another way to look at the periodic table is by separating the elements according to the 4 different electron sublevels. Notice that the number of columns or families in each block exactly matches the number of electrons that occupy that sublevel. On the far left we have the S block consisting of 2 columns because the S sublevel contains 2 electrons. To the right we have the F block and the D block. On the far right we have the P block consisting of 6 columns. We will now take a look at periodic trends, which are consistent and predictable changes in elemental properties. We can see these as we move across a period or down a chemical family. The first trend we'll look at is atomic size. In the quantum mechanical model, the outer boundaries of an atom depend on the size of a charge cloud in which electrons spend approximately 90% of their time. This means that the sizes of individual atoms are not hard and definite, though we can estimate them based on how close they get to one another when bonds form between them. The two common definitions of atomic size stem from the classification of elements into metals and nonmetals. For nonmetal elements, which commonly occur as diatomic molecules, atomic size is defined as the covalent radius, which represents 1/2 the distance between the two identical nuclei in the molecule. The process of estimating the atomic size of metals is very similar to that of nonmetals. Metal atoms pack together in the solid state to form a crystal lattice. Half the distance between the identical nuclei of adjacent metal atoms is defined as the metallic radius. As for what actually influences the sizes of atoms and ions, we have two opposing factors. The first factor is the number of energy levels present. As the number of energy levels increases, the probability that outer electrons will spend more time further from the nucleus increases, and so the atoms become larger. The other factor is the amount of nuclear charge felt or seen by the outer electrons. As this effective nuclear charge increases, the outer electron cloud is pulled closer to the nucleus, and the atom becomes smaller. Note that chemists use the symbol ZF to refer to the effective nuclear charge. From this depiction of the relative atomic radii of some of the elements, we can see two clear patterns in how the size changes across periods and down families. First, as we move down a family or group, the sizes of the atoms generally increase. This is because as the value of n increases for each new element, a new inner electron level is added between the nucleus and the atom's outer electron cloud. Even though the positive charge on the nucleus is increasing, each additional inner level of electrons effectively shields the outer cloud from the attractive force of that nucleus. The additional inner electron clouds also repel each other. Second, as we move across a period, the sizes of the atoms generally decrease. When we move from left to right across a period, the electrons are being added to the same outer level. The level of shielding by the inner electrons therefore remains the same, and the added electrons are ineffective at shielding each other from the increasing positive charge on the nucleus. As a result, ZF on the outer electrons increases, and the charge cloud is pulled closer and closer to the nucleus, decreasing the size of the atom. There are exceptions to these general trends, and they can be explained by considering the electron configurations of the atoms and the electron sublevels being filled in each case. Looking at period 4 as an example and moving from left to right, we start filling the fourth energy level at potassium, and the atomic size shrinks for the first two elements as we'd expect. When we arrive at the transition elements and begin filling the 3D sublevel, however, the sizes remain relatively constant. Remember that n equals 3 electrons spend most of their time closer to the nucleus than n equals 4 electrons. This means electrons in the 3D sublevel are capable of shielding the 4s electrons from the increasing nuclear charge as we move across the period, and ZF would be reduced. For example, even though zinc has a nucleus with 7 more protons than vanadium, the extra shielding provided by zinc's 10 electrons in the 3D sublevel is such that zinc's atomic radius is approximately equal to vanadium's. The same forces that influence the sizes of atoms also influence the sizes of ions. For example, let's rank the following species in order of size from largest to smallest. All of the ions have the same number of electrons, 10, so we can assume that the amount of shielding is also the same for each. This means the attractive force from each nucleus is the only factor influencing the difference in size of each species. The greater the number of protons present, the stronger the attractive force on the electron cloud, and thus the smaller the atom or ion. Therefore, if we rank the species in order of decreasing positive charge on the nucleus, this ranking scheme will also represent the order of decreasing size, and our answer is the following. The next trends we'll look at are the trends in ionization energy. Ionization energy, often shortened to IE, is defined as the minimum energy required to remove an electron from a gaseous atom or ion. The term is often used to mean the first ionization energy, whereby a neutral atom becomes a 1+ cation according to the following equation. Ionization energy tells us how strongly an atom holds on to its outermost electrons. For instance, an element with a low first ionization energy will be more likely to lose electrons and form cations during chemical changes, while one with a high first ionization energy might have a tendency to gain electrons and form anions, or perhaps not form ions at all. The general trend is that as atomic size decreases, ionization energy should increase, since large atoms whose outer electrons are held less tightly would have lower first ionization energies than smaller atoms whose outer electrons are held much more strongly. Thus, as we move down a group, the first ionization energies tend to decrease, while as we move across a period they tend to increase. Note that lower ionization energies are associated with elements nearer the left side of the periodic table, namely the metals, which generally tend to lose electrons in chemical reactions, while nonmetals on the right side have relatively high ionization energies and tend to gain or share electrons rather than lose them. The noble gases, of course, do neither of these things. There are a few notable exceptions we should cover that can be explained by analyzing electron configurations. For instance, even though oxygen is smaller than nitrogen, oxygen has a lower first ionization energy. This arises from the fact that while nitrogen has a single electron in each of its 3 2p orbitals, and a half-filled p sublevel that's quite stable, oxygen has a pair of electrons in one of its 2p orbitals. The increased electron-electron repulsion from the pairing makes it easier for oxygen to lose one of those electrons when first ionized. In addition to helping us predict which elements might tend to lose or gain electrons during chemical changes, ionization energies also help us to identify which electrons are likely to be associated with those changes. After removing one electron from an atom, further ionization energies increase, since each successive electron removed is being separated from an increasingly positive ion. The increases are not regular, however, since whenever the last outer electron is removed, inner or core electrons are now involved. This means the next ionization requires significantly more energy. We can see this by looking at the first 3 ionizations of beryllium. Once the second electron is removed, a dramatic increase in energy is required to remove the third electron, reflecting the fact that it is an inner or core electron. Core electrons are bound much more tightly to the nucleus and thus do not take part in chemical reactions. To finish off this section, we'll look at trends in electronegativity. Electronegativity, often shortened as EN, is defined as the relative ability of a bonded atom to attract shared electrons to itself. For instance, atoms with relatively high electronegativities tend to pull bonded electrons closer to their nuclei. In addition to dictating the nature of the chemical bonds that form, electronegativity also plays a role in determining the properties of the compounds containing those bonds. A clear resemblance to the trends in ionization energy can be seen when looking at the general trends in electronegativity. Electronegativity increases going across a period and decreases moving down a group. Note that the noble gases don't have EN values because they don't generally form chemical bonds. The electronegativity values are numbers ranging from a low of 0.7 for cesium to 4.0 for fluorine, and were determined by the American chemist Linus Pauling. We'll now move on from our discussion on trends and dive into the topic of spectroscopy, which is a process that's used to probe matter using various elements of the electromagnetic spectrum. The electromagnetic spectrum consists of a continuum of energies of different wavelengths. Visible light makes up a small portion of this continuum and includes wavelengths ranging from 380 to 750 nanometers. Light, which is a form of electromagnetic radiation, can be emitted in the form of a wave from a source and absorbed by various forms of matter. At the atomic level, light energy is released or emitted when excited electrons fall to a lower potential energy state. Light that's emitted when an electron falls from a higher energy level to a lower energy level is called a photon. The energy of a photon is quantized, which means that photons that exhibit a certain frequency of light have a fixed amount of energy. The energy associated with photons is always conserved, according to work done by Max Planck. The energy can be calculated by multiplying the frequency, denoted here by the lowercase Greek letter nu, by Planck's constant. Although wavelength and frequency vary across the electromagnetic spectrum, the speed of this radiation is fixed and is equal to the product of the wavelength, denoted here by lowercase Greek letter lambda, and the frequency. This constant, c, is the speed of light, about 3 × 10⁸ meters per second. Looking again at the electromagnetic spectrum, we see that there are other types of electromagnetic radiation besides visible light. On the far left we have gamma rays, which have the greatest energy and frequency. They also have the shortest wavelengths. On the far right we have radio waves, which have the lowest energy and frequency. They have the longest wavelengths, varying from just below a meter to infinity. We'll take a deeper look at these types of electromagnetic radiation as we go through several types of spectroscopy. First, we have nuclear magnetic resonance, often shortened to just NMR, which involves radio waves. These waves oscillate at very low frequencies, from hundreds of gigahertz down to tens of kilohertz, and are relatively low in energy. When radio frequency radiation interacts with matter, there's no effect on electrons since their orbitals are separated by more energy than a radio wave can deliver. Radio waves can't impact the position of the nucleus of an atom or the bonds in a molecule either, but they can cause a change in nuclear spin. Nuclear spin is caused by the angular momentum of neutrons and protons, and is analogous to electron spin, which is a quantum property of electrons and a form of angular momentum. The combination of spin and charge of the nucleus creates a magnetic moment which essentially behaves like a quantum mechanical compass needle that may align either up or down with an applied magnetic field. If the nuclei of a sample is placed in a magnetic field and just enough radio frequency energy is supplied to reorient the spins, every time a spin flips we observe a nuclear magnetic resonance. The internal magnetic fields within a molecule differ at each chemically distinct site. Each signal, or peak, or group of signals in an M&R spectrum is due to the nuclear spin change of a hydrogen atom in a distinct environment within a molecule. An NMR spectrum can help reveal the structure of a molecule, and they are commonly used in the identification of organic compounds. This is as far as we'll go with NMR though, as the recognition of functional groups and other compound characteristics following the observation of an NMR spectrum is far beyond what is required in a course such as AP Chemistry. Between radio waves and visible light we have infrared radiation, commonly shortened to IR. The prefix infra essentially means below, and we can see that the frequencies and energies of infrared light are below that of red light. With higher energy and frequency than radio waves, however, the electric force accompanying an infrared wave is actually able to push and pull the nuclei within a molecule. The absorbance of an infrared photon causes increased forces of attraction between nuclei and electrons, and increased forces of repulsion between nuclei. This leads to bonds stretching, compressing, and bending, or vibrating, in the infrared range of frequencies. Bonds experiencing these forces are undergoing resonance. Nuclei attached to bonds may be likened to masses attached to springs. Strong bonds are like stiff springs and vibrate more rapidly. Heavy nuclei are like heavy masses and vibrate more slowly. However, it's important to realize that this spring bond analogy has limitations because molecular bonds are quantized and can only vibrate with discrete energies. In IR spectroscopy, the energy of infrared photons can equate to the difference between two allowed levels of vibration, exciting a molecule from one allowed state of vibration to another. In a molecule, each bond has its own unique difference in energy corresponding to the strength and elasticity of its vibration. This means that a bond between two particular atoms will vibrate at nearly the same frequency in any molecule in which it's found. A vibrational spectrum is a series of bands, each resulting from a different functional group or portion of the molecule, and is like a fingerprint for the molecule. A functional group is some combination of atoms in molecules which undergoes characteristic reactions itself, and may influence the reactivity of the rest of the molecule. For example, carboxyl groups, which are present in carboxylic acids. Moving up from infrared radiation in terms of energy and below in terms of wavelength, we have visible radiation, which is the segment of the electromagnetic spectrum the human eye can view. The portion of the spectrum with wavelengths below 400 extending down to around 10 nanometers is called ultraviolet. The prefix ultra can mean beyond in space or on the other side of, and in this case ultraviolet is just beyond violet-colored light. Within this region, photons may affect the most weakly held electrons, the so-called valence electrons. They may be excited out of their energy levels and chemical bonding may be affected. The behavior of these valence electrons is to a large extent governed by Coulomb's law. This relationship between the force on two charged objects, the charges and the distance between them, was determined in 1785 by French physicist Charles-Augustin de Coulomb. The law resembles Newton's law of universal gravitation and is sometimes referred to as the inverse square law. From this we see that as the charge on one or both objects, such as a nucleus and an electron, increases, so does the force of attraction, while as the distance between an electron and the nucleus increases, the force of attraction decreases. We can use this law to explain most of the atomic and ionic trends in the periodic table. The valence electrons have the greatest R value and are screened most effectively from the charge on the nucleus. The reduced charge experienced by the valence electrons is sometimes referred to as ZF, or the effective nuclear charge. ZF equals Z, the atomic number, which is effectively the number of protons, minus the number of screening electrons. The screening electrons are all those found in energy levels below that of the valence shell. This equation indicates that the effective nuclear charge is essentially constant moving up or down a family in the periodic table. However, it definitely increases moving across a period. The reduction in the nuclear charge felt by a valence electron is often referred to as the shielding effect. While explanations of nuclear and ionic trends such as ionization energy and radii should be centered on Coulomb's law, an explanation of ZF and the shielding effect are definitely appropriate. UV-vis spectroscopy involves absorption of light by the valence electrons which occupy orbitals far from the nucleus and are high in energy. Consideration of Coulomb's law and the shielding effect tells us that these electrons are attracted by an attenuated and distant nuclear charge, so they're the easiest electrons to disturb. They may be ionized and, under milder excitation, may be promoted to higher levels of energy, basically moved from their ground state to an excited state. Transition metal ions may experience movement of electrons between d orbitals of different energy levels. Such movement may be accompanied by the absorbance or release of visible light of specific wavelengths, which is why compounds containing transition metal ions with partially filled d orbitals produce color. Ultimately, the main idea here is that energy in this region of the electromagnetic spectrum can promote valence electrons. Sometimes a valence electron may be completely removed, resulting in the creation of an ion. This process is called photoionization. Such an ionization caused by light is also called the photoelectric effect. Core electrons, which are those below the valence shell, are considerably more difficult to remove from their atom since they're attracted to a poorly shielded, more positively charged nucleus, and exist in orbitals that are lower in energy, so their average distance from the nucleus is considerably less than that of valence electrons. Their removal requires more energy than ultraviolet or visible radiation have. An X-ray photon, however, can supply sufficient energy. This brings us to the final type of spectroscopy we'll look at and spend the most time on, photoelectron spectroscopy, shortened to PES. This was formerly known as X-ray electron spectroscopy or XES. A simplified model of the process is shown here. It involves the use of a device that focuses a monochromatic beam of X-rays at a solid sample so that random atoms in the sample may release electrons from any energy level. The emitted electrons are collected by a lens and passed through an electron energy analyzer, which measures the kinetic energy of the electrons. The electrons then reach a detector and a computer visualizes them in the form of a photoelectron spectrum. The energy of the X-ray photon can be calculated as Planck's constant times its frequency nu. This means the energy required to remove an electron from an inner energy level of an atom is simply the difference between these two values. This is virtually identical to the one used to determine the first ionization energy of an atom, except that very high energy UV or X-ray photons are required to emit core electrons. Occasionally, the vacant orbital produced by an ejected electron may be filled by an electron falling from a higher energy orbital. The energy from such a fall may cause the emission of another X-ray photon, or it could be absorbed to cause the emission of a second electron. These are called Auger transitions and require a more complicated calculation. Photoelectron spectra consist of a series of peaks where intensity is plotted on the y-axis against the energy, E, needed to eject an electron on the x-axis. Some PES spectra show energy increasing on the x-axis, though the most common convention is to show energy decreasing from left to right. The height of each peak in a PES spectrum is directly proportional to the number of electrons of equivalent energy. The energy units used are megajoules per mole, though electron volts per mole is used less commonly. Because actual PES spectra contain extraneous peaks, referred to as noise, that are not useful to us, we'll just look at simulated PES spectra. The following simulated photoelectron spectra of elements 1 through 5 in the periodic table have been adjusted so we can directly compare the peak heights. This would be the case if all the spectra were produced using equivalent sample sizes. We can use the number of peaks in a PES spectrum to determine the number of orbitals existing in an element. Each peak represents an orbital, so the number of peaks equals the number of orbitals. The magnitude or height of a peak is directly related to the number of electrons in the orbital the peak represents. The smallest peaks represent s orbitals, and full p orbitals are 3 times the height of a full s orbital. For instance, a full s orbital contains 2 electrons while a full p orbital contains 6 electrons. It follows that a full d orbital is 5 times the height of a full s orbital. A full orbital is twice the height of a half-full orbital. Also, the highest energy peaks appear farther left and represent electrons in orbitals that are closer to the nucleus. Examination of each of the spectra provided thus far indicates that the energy required to remove the innermost electrons varies significantly from element to element. As the atomic number increases, we see that the binding energy does as well. The principal explanation is that the effective nuclear charge, ZF, increases as we move to the right across a period, so the energy required to remove the innermost electrons increases. Note that this is not only true for the 1s orbital electrons, but also holds true for the 2s and 2p orbitals. As a quick practice, let's identify the element represented by this PES spectrum. Right away we can see that there are 5 peaks in total. The innermost peak represents the 1s orbital. It has the highest binding energy. Going from left to right, the other 4 represent the 2s, 2p, 3s, and 3p orbitals. The 1s, 2s, and 3s orbitals are all full, and since the 2p peak is 3 times the height of the full s orbitals, it must also be full. The 3p orbital, however, is only 1.5 times as high as the full s orbitals, so it must contain 3 electrons. This electron configuration matches that of the element with atomic number 15, which is phosphorus. To wrap things up, here is a table which summarizes the most important information of each spectroscopic technique: nuclear magnetic resonance, infrared, ultraviolet and visible light, and photoelectron spectroscopy. The region of the electromagnetic spectrum they use is shown, as well as what the photons are used to do.